Hello. In this video, we're going to talk about some essential concepts that are really important to kind of start to get your head around as you begin to program. We call it a beginning because really a lot of the definitions at this point are just a foundation to start to build upon. So we just want to have a general idea of how to define different things, but also to recognize that, you know, as you start to dig deeper into these ideas, they're quite complex, and you can actually, in some cases, have entire courses about them. So, with that said, let's dive in. Essential concepts, a beginning. So, there's some common vocabulary and concepts we want to kind of start to get our head around, like I just said. And one of the things I want to stress at this point with this course is that this is a programming course. In many ways, it's a language course, and using the correct language is really beneficial, because if you use that correct language, it's going to allow you to transfer your skills a lot easier. So whenever you're working with someone, really make an effort to use the correct terminology. And also remember that just because someone doesn't know how to program, it doesn't mean you can't explain something to them, because often this vocabulary is accessible to many people in an introductory context. So, like I said, it's helpful to start to develop an understanding of some essential terms as they're regularly used by programmers. And we're going to start to develop the definitions to help us get us going. So in no particular order, here are some of the things by the end of this PowerPoint we want to talk about. What is an algorithm? What is a programming language? What does compile mean? What is a function/method? What is tracing a program? How does a programming language work? And this is a personal opinion, but I really believe that asking the right questions will lead you to the answer. You know, often when we think about learning, we think about knowing the answer. And I think it's a far more productive process to think about finding the right questions. Because if you know the right questions, you can then start to find your answer. And with programming, often there's a lot of tools online that are pre-built to do what you want to do. So let's start off with how a program works, in short. So imagine we have two people. One person standing up on the left, and the other person is sitting down on the right. And the person on the left wants to tell the person sitting to stand up. So they say, "Stand up, please." And that's what they say. Now, I don't know if Google Translate is perfect, but the person on the left is speaking English and the person on the right is speaking Russian. And so they can't communicate. And that's kind of what happens between a human and a computer. And to solve this problem, what we do is we basically find someone who speaks English and Russian. So the person says, "Stand up." They translate to Russian. The person says, "Okay," and they stand up. This is a really simplistic view of how a program works, because we're going to program in English, and then it needs to be translated into something the computer can understand to then execute. So if we imagine this person sitting at a computer, they might say, I want the light to turn on when it's dark outside. So they type a little bit. That gets converted into some binary or machine code, and then the light turns on. You know, the computer can't understand the request, "turn on light." But that request can be translated into something the computer can understand. And in our course, we will actually be able to do this. There's some hardware involved, and we're going to kind of explore that a little later. And just as a side note, that's the actual conversion to turn on lights from English to binary. And you can find the link to that converter right there. And it's a neat program to write if you're ever looking for a fun little tool to develop. So now let's talk about what a programming language is. So a programming language is a language that can be used to instruct the computer to do something. So we talk about the syntax of a language. And the syntax of the language is a set of rules used to define a language. And that's not just for computer science, that's any language. All languages have syntax around them. And there are a lot of similarities between those syntaxes, but there's also, they look very different at times. And like I said here, the syntax looks very different at times between languages. But I would argue that more often than not, the syntaxes are very similar. And what's really important to recognize here is that programming languages evolve and change to suit the needs of the programming community. So we're using Python 3 in this course. And I think the iteration right now is Python 3.5. You know, Python 3 looks very similar to Python 2. In fact, it's almost indistinguishable unless you know what you're looking for. But that's because the language has evolved and changed to suit needs. In the same way, new structures are added. So, for example, with Java, I think when Java 8 was introduced, a new type of loop was introduced to the language because it provided the means to do something in a simpler manner. So here are some examples of programming languages. We have Java, we have C++, we have Python, we have assembly. These are all different types of languages, and there's lots of programming languages out there. I really want to stress the point that there is not a best programming language. Different programming languages are better in given situations, but you really want to avoid that idea that there's one language that is the best language. So back to how a program works again in short. So the idea is, we talked about this idea of we give an instruction, it gets translated, and then the computer does something. What a computer does, the way we can talk about that is we have our source code that gets compiled, and the process of compilation is changing the English syntax into machine code, we could say. And again, that's a simplification, of course, but that's essentially what happens. Is we write our code, we compile it, and then we execute it. And it's the same thing with Python. Now, it's important to note, Java and Python do deal with that differently, and there's actually some really important concepts here. But for our purposes at this stage, we just want to understand that we compile a program, and then we run a program. And I encourage you to kind of look more into this, because it's really interesting, that process of compilation. So tracing a basic program essentially is you start from the top and work your way down. There are different ways to indicate where a program starts, but a lot of what we do in this course is we'll look at small little code segments and talk about what's happening. You might have no programming experience at all, and there's a good chance you might be able to work through most of this, with the exception of maybe those last 3 lines. So let's trace it. So the first line there creates an integer, and it calculates the number 6 and puts that into memory right there. The next line creates another integer called b, puts 21 in it. The next line creates another integer called c, and puts 12 in it. And all that's happening is we're just evaluating the right side of the expression, and then whatever we get, we put into the left side variable. And now we're doing the same thing. So here, there's a value of b that's been defined, and a value of c that's been defined, so we add those together and put it in a. Same thing here, we add a and c together and put it in b. We add a and b together and put it into c. Now what's important here to understand is that we're tracing the program from top down. And programs don't solely run from top down, but initially we're going to look at them in that way. But what we want to remember is that every time we rewrite a variable, that value gets changed forever. So c was initially set to 12, and then once this line is completed, c will change to 78. And so now, these 3 lines here are how we tell a Java program to print something out to the console. So it's a way of printing out text. And so it's going to print out A is 33, B is 45, and C is 78. So that's a simple program trace. And it's important not to be intimidated by when you look at them. Take some time and go step by step. I often like to take a ruler when I'm looking at code and hide everything below it and kind of look at that one line and then think about what's happening and work my way down. So here's another program. This one's in Python. And you're going to look and hopefully recognize that they look really similar. And in fact, this does the exact same thing. So there are, of course, some differences here, and we'll talk about what those differences are. But it's the exact same idea. We're tracing it from the top down, and then we're putting the values into the correct variables and printing them to the screen. So what I really want to stress here is that there are 2 programming languages, and for all intents and purposes, they look the same. Their syntax is just slightly different. Okay, there's the part where we declare and initialize variables. There's the part where we assign variables new values. And there's the part where we print them out to the screen. So you'll notice that Python, it's a lot easier to print things out than in Java. And it looks slightly different, but it's the same principle. Again, you're going to hear about what language you should learn. And I really want to stress that there's no language you should learn. There's no best language. All programming languages, for the most part, are useful in a certain context. And that's, again, a really important piece. You want to focus on the structure and the logic of the language. Okay, good programmers are able to transfer skills between languages, and that is really the focus of our course. So An algorithm is a set of steps that will result in a specific outcome. A recipe is an algorithm. If you follow the directions to make a cake, you should end up with that cake, in theory. I know it's not always that. That's not always the case, especially with my baking skills. But the point I'm making is that an algorithm is simply a set of steps that are followed to get a desired outcome. It's important to understand that algorithms aren't a computer science thing. Algorithms have been around long before computer science existed as a subject matter, and in fact, long before computers even existed. Algorithms are just a set of steps you follow to get to an end result. Algorithms are always being developed and refined. This is something that is happening all the time, and it is one of the reasons that we've seen such amazing growth in all the applications and games and various things we use in the computer world. People use other people's programs all the time. It's really, someone will write an algorithm, then someone else will use it. Often what will happen is that algorithm will sit inside a function or a method, and then someone can import that into their program. So really briefly, a function or a method is a small little component of code that can be called upon and used by someone. And a nice example is Pokemon Go. Pokemon Go uses the mapping algorithms developed by Ingress for setting up their mapping component of the game. So there are lots of really cool algorithms, and as you study computer science, you start to learn some common ones that are out there. So I have listed here on the right-hand side 5 algorithms that you may or may not come across. I want to clear that these algorithms are used for lots of different things, and that they are by no means all of the algorithms that are out there. But there's a bilateral algorithm. I actually heard about this one when I was watching Star Trek Enterprise, Season 1, Episode 21 at 15 minutes and 36 seconds if you're interested. So I heard them talking about it, and I did a little searching about it, and it turns out the bilateral algorithm is used for removing the noise in images. So it's used for cleaning up pictures. That's one of the reasons why I love Star Trek. There's some real science in there. They just ignore some properties of real physics. A-star algorithm. A-star algorithm is an algorithm that can be used for maze tracing. So very often a version of this algorithm will be implemented if you have a game where there is some sort of AI following you. So you're playing that classic game where you're in a maze and then someone's chasing you. An A-star algorithm is one possible algorithm to allow that person to follow you in that maze. Backtracking algorithms. These are types of algorithms used for a variety of different things. They're often recursively implemented algorithms. And so, for example, a backtracking algorithm would be a type of algorithm used to clear the board if you're playing a game like Minesweeper. And it's also a basis for developing route optimization programs. So if you have 20 stops that you need to make when you're traveling and you want to find the optimal route to do that, you might use a backtracking algorithm, or develop an algorithm that is based on backtracking algorithm theory. The last two, insertion sort or merge sort, are two very common sorts that are known in the computer science world. It's important to actually understand sorts if you do pursue computer science as a field. Sorting and searching is a fascinating topic to explore. And I do encourage you to not hesitate to look up some of the popular sorts that are out there. Again, at this point, we're not interested in the implementation of any of these algorithms. I'm just trying to really kind of drive home that point that there are lots of algorithms out there, and programmers are always kind of learning about new algorithms and putting them in their back pocket to use at later times. So let's look at an actual algorithm that exists. Euclid's algorithm is a famous algorithm used for finding the greatest common divisor of two numbers. Now, I'm not going to go through all of this in great detail because this is not about me teaching you Euclid's algorithm. But what I'm trying to stress is that there's lots of ways to look at an algorithm. We might look at it as a flowchart. So if we follow this flowchart, so we pick a number A and B, and then we kind of follow the logic here, we're always going to end up with the greatest common divisor of two numbers. And so given this algorithm on the left-hand side, I can take two numbers and follow that process and figure out that the greatest common divisor of 24 and 12 is 12. Now that said, you can probably do that without this algorithm, but what if your numbers were very, very large? It's really useful in this case. Where computer science or computers become and programming becomes really useful is that you can program these algorithms to deal with any numbers. So you can program what's called a general case. So now what you can see here is this is a general case implementation of Euclid's algorithm in Java and a general case implementation of Euclid's algorithm using Python. So I can now give any two numbers and immediately get the greatest common divisor of those two numbers. One of the things we'll do a lot of is developing simple algorithms. And a really good first step to developing that general case is to start off with a specific case and just to see how the mechanics work. And we'll talk more about that as we learn more about algorithms. So again, there's a lot of places that algorithm development is really useful. You're going to come across a lot of really interesting problems where you're going to go through this kind of algorithm development. Very often in math class, we're developing different algorithms to do things. And one of the interesting things you can do with computer science is if you can generalize those algorithms you're developing in math to solve a problem, you can then put that into a computer and you can solve a whole bunch of problems with different numbers. So here's a great kind of problem that you might want to develop an algorithm for. So if we list all the natural numbers but below 10 that are multiples of 3 and 5, we get 3, 5, 6, and 9, and the sum is 23. So we want to write an algorithm to find the sum of all the multiples of 3 or 5 below 1,000. So you could do that by hand, but you're probably better off to write a generalized algorithm and then have a computer process that. Here's another nice one. Again, I'm not interested in the actual algorithm. I want to be clear on that. I just want to kind of highlight that point that these types of problems are really conducive to generalized algorithms that can be used to solve the problem. And then you can make the problem more complex, larger in terms of scope or smaller, and very quickly come to an answer. In fact, to solve this problem here, you use a backtracking algorithm to do it. So, as always, if you have any questions, please don't hesitate to ask. And have a wonderful day. Take care.